Hello and welcome to direction fields. So the idea here, a differential equation that we have the first derivative is equal to some function. So, oops, a differential equation of the form y prime equals f of xy is essentially giving us the formula for slope. Right? So this is essentially giving us the formula for slope. I apologize if you can hear other conversations in the background. I hope they're not particularly loud. Basically, if we have the equation for slope, then we can plot sort of a bunch of little lines which are acting like tangent lines at whatever point we want on a coordinate grid. So we can plot mini tangent lines. That's not how you spell mini. We can plot mini tangent lines. At various points in the coordinate system. And this gives us a direction field, or sometimes referred to as a slope field. So this will be the direction field. So we're going to plot one by hand here. Primarily, we'll be using technology, so we don't have to calculate slope at a whole bunch of different lines. But we're just going to plot a little bit of the direction field for y prime equals xy. So for example, for any point of the form, if we have here xy as our point, and then we find y prime at each point, for any point of the form 0y, whatever y is, right, 0 times y will give us 0. So any point with an x coordinate of 0 should have horizontal slope, right, or slope 0. So for we're just going to draw a bunch of horizontal mini lines that should act like the tangent lines at each of those points, right? And then similarly, for this particular equation, anything in the form x comma 0 also will have slope 0. So anything on the y-axis will also have slope 0. And then the rest we'll kind of have to figure out, right? So if we do say x is equal to 1, and I'm going to just do y is y, we'll get y for the slope, right? So for x equals 1, we'll have slope 1 when y is 1. We'd have slope 2 when y is 2, slope 3, the lines are getting steeper and steeper and steeper. We'd have slope -1, then -2, then -3. Again, the lines are getting steeper and steeper in the negative direction. Then for x being -1, we just get out -y, right? So for y equals 1, we'd have a slope of -1. For y equals 2, a slope of -2, -3. And then y equals -1 would have positive slope, and we just get steeper as we go, right? And we could do this going through point by point by point. So for x equals 2, we'd have slope 2, and then 4, and 6, right? And then there'd be negative on the side. And so you can kind of see as we work our way out and up, the line slopes or the tangent lines get steeper and steeper and steeper. Okay, so as we work our way out and up, our tangent lines get steeper and steeper and steeper. And we could keep that going. And so this is a very rough sketch of a direction field. Now, what we can do from here is we can kind of sort of follow the mini tangent lines and get a basic idea of what a curve might do. So this next part will do that. So next up, I have already produced the direction field for y prime equals x plus y. And we are going to sketch what are called solution curves. So in order to do this, we are going to essentially follow the tangent lines to form a curve. So for example, if we start here, we'll start off with sort of a fairly shallow slope. And then it looks like our lines are kind of flattening out and then going up, right? So we're going to sort of turn around. And then as we move to the right, our lines get steeper and steeper and steeper. So now we're kind of parallel to the line next to it. And then we sort of parallel to the line here. And our curve just works its way off the graph. We can also work our way backwards. So the line started off fairly flat, and then it kind of slants a little bit more. And as we go, it looks like it would go off this way. Right? So we're just kind of tracing what those little mini tangent lines appear to be doing. If you notice, we have a bunch of lines that just run straight into each other that seem to just form a dashed line. So let me just pick a new color for that. So along here, it appears we essentially have a dashed line, and our tangent lines just go straight from one to the next to the next. So it looks like that solution is just a straight line. Okay. I'm going to pick another curve that say starts here. So we start off with that slope, and then as we move to the right, our lines seem to be kind of flattening out. So we work our way kind of matching the slopes of the tangent lines nearby, follow the pattern. Now we're working our way back up based off the tangent lines, and as we go, we get steeper and steeper. And then if we backtracked, as we work our way left, it looks like we'd kind of come in along the green line I drew. We shouldn't ever cross that green line because those points go just perfectly in that diagonal green line we drew. So here are a few solution curves, and then let's just see what happens if we look under the green line instead of above it. So looking under the green line, let's just start up high here. Now we have a downward slope that's going faster than the green line. And as we work our way away from the green line, those slopes seem to be getting just a little steeper and a little steeper. And so here we kind of work our way down off of the page. if we do another, let's say we start here again, we follow those tangent lines down, and we are essentially working our way just down to the bottom of our coordinate system. So these are a series of solution curves. Technically, if I continued these on forever, the purple one would just kind of run closer and closer to the green line till we go off. The green line technically should just keep going. But these are essentially following those little mini tangent lines, we can get a pretty good idea of what solutions might look like. So this is sort of basic direction fields. In the next video, we will see how to use a computer program to generate the direction field and solution curves for us.